Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. I'd like to start off by thanking everyone who's taken the time to check out our new Facebook and YouTube pages over the past couple of weeks. We really enjoy hearing from listeners, whether via Facebook, YouTube, Twitter, or email, so please continue reaching out to us. We'd also like to say thanks to the folks over at O'Reilly who provided us a ticket to give away for next week's Strata plus Hadoop World Conference. With that being said, we do have a winner to announce. Congratulations to Evan Wright. Evan is a principal data scientist at security startup Anomaly, and he'll be receiving a bronze pass to the conference. Looking forward to meeting you, Evan. Thanks to all who participated, and be on the lookout for more contests in the near future. Speaking of events, last week I announced one that I'm organizing, and I hope you'll check it out. It's called the Future of Data Summit, and it'll be taking place in Las Vegas in May at the Interop ITX conference. To give you a taste of the great content I'm pulling together for you at the event, last week's podcast featured James McCaffrey of Microsoft Research, who's just one of the 15 great speakers you'll hear from at the summit. We'll be covering a bunch of really exciting topics, including, of course, machine learning and AI, but also IoT and edge computing, augmented and virtual reality, blockchain, algorithmic IT operations, data security, and more. You can learn more about the summit at twimlai.com/futureofdata. And now about today's show. This week, my guest is Shubho Sengupta, research scientist at Baidu. I had the pleasure of meeting Shubho at the Rework Deep Learning Summit earlier this year, where he delivered a presentation on systems challenges for deep learning, and we dig into this topic in the interview. Shubho has tons of insights to share into how to do deep learning at scale. And even if you're not operating at the scale of Baidu, I think you'll learn a ton from our conversation about architecting, productionalizing, and operationalizing deep learning systems. We also spent some time discussing the role of GPUs and hardware in building scalable machine learning systems, and that's an area he has a lot to say about as the author of the CUDA-PP library, the CUDA Data Parallel Primitives Library, which was the first parallel programming library for GPUs. And now, on to the show. Hello, everyone. I am on the line with Shubho Sengupta, a research scientist at Baidu. Shubho and I met at the Rework Deep Learning Summit in San Francisco last month. I really enjoyed his presentation on systems challenges for deep learning, which did a great job of talking through some of the challenges associated with deep learning at scale. And I'm very grateful to Shubho for agreeing to join me on the podcast to discuss his presentation at the summit and as well as some of his other work. So welcome, Shubho, and thanks so much for joining me on the podcast.
Thank you, Sam. Thanks for having me.
Yeah, I'm really looking forward to this conversation. There were a bunch of really good presentations at the summit, but as a guy who found his way to machine learning and AI, but also spends a lot of time thinking about cloud and big data infrastructure, yours really spoke to me. So I'm looking forward to digging into it.
Thanks. I was a little bit afraid that people won't like it because it was a little bit off track in some sense.
No, I thought it was fantastic.
Thanks.
Yeah, why don't we start with having you share a little bit about your current role at Baidu and some of the things you've done previously and how you got involved in machine learning and AI.
Sure. So as you said, I'm a research scientist at Baidu Silicon Valley AI Lab. And I've been with the lab for the past 2.5 years, a little bit more than 2.5 years, almost since the inception of the lab. I primarily work in speech and language. I would say more speech than language. Over the last 2.5 years, I've primarily worked on what is called ASR, which is the piece of technology that takes voice as we speak and then converts it into text. And we have built one of the best English ASR systems and by far the best Mandarin ASR systems, which powers most of our products in China. And currently, I'm starting to work on other things like speech synthesis, a little bit of language modeling to keep in the same domain. Surprisingly enough, I actually did not start in speech. I started my career, so to speak, in computer graphics. I was very, very interested in special effects in films. And I know this sounds a little bit like a fairy tale, but I came to do a PhD in computer science to this country because I was so blown away by the films that Pixar was making. So my goal was, if I get to grad school, maybe I'll get to work at Pixar at some point.
And did you ever work at Pixar?
I did. I spent 6 months as an intern at Pixar developing some of the early kind of GPU assisted what are called relighting tools. These tools give you a fast preview of the film scenes that the lighting designers are using to relight the scene.
Okay.
And that was an incredible experience. I still very fondly look back on that experience. I think it was back in 2006. That's a while ago.
Okay.
But it still sticks in memory. And
I bet.
That's kind of what I started taking these GPUs that were only used for playing games and starting to use them for doing general purpose compute because, I thought of graphics as just another computation domain. So during my PhD, I came up with all the basic parallel algorithms that people use to program GPUs. So I was very lucky that I was very early in this field and made a lot of impact. Was the author of the first parallel programming library for GPUs, and did a lot of basic algorithm work on GPUs. So, I've been with GPUs for 12 years now, almost since the early days when they were very, very hard to program for general purpose compute. They're primarily used for graphics. So it's very heartening to see that, so many different areas being so positively impacted by GPUs.
I bet. What was the name of the library that you worked on?
CUDPP, CUDA Data Parallel Primitives Library. It's still around and not so much popular anymore because a lot of other libraries like Thrust, etc., which is good because other people have. Once you leave grad school, it's very hard to keep on contributing code to that library because you have other engagements, a full-time job, etc. But my advisor and his students are still putting in new algorithms into the library, so it's still around. People still use it. And that library itself has spawned other efforts like Thrust from NVIDIA and Modern GPU also from NVIDIA.
Okay.
And I should also give a shout out to NVIDIA because NVIDIA had been extremely kind in financial terms and in resources throughout my research career, and I still work closely with NVIDIA even though I don't work there, but I work with a lot of people at NVIDIA on almost a day-to-day basis.
Well, feel free to give that shout out to NVIDIA because, in fact, I was at a conference last week where a speaker from NVIDIA gave a shout out to this podcast.
Awesome. Awesome. Yeah, NVIDIA has supported my career ever since, literally my first day of grad school. My first day, I think my first week in this country, I was at a talk at NVIDIA because my advisor was there. One of his students was giving a talk. So it was in 2004. So it's been a while, but the relationship is strong.
That's great. So my thinking for this conversation was that we would really dive into the systems types of issues. But given your expertise in GPUs, I have so many questions about kind of GPUs and how they're used in ML and AI and some of the libraries that support them. So at some point, we want to make sure to touch on that stuff as well.
Yeah, absolutely.
So in your talk, you gave a specific example of a speech recognition that you worked on that had some interesting challenges. Can you talk a little bit about that project, or one of the a specific type of project that you can talk about?
Yeah, sure. So we have primarily been working on ASR, which is essentially speech recognition, for the past 2 years or so. And when we started, one interesting thing about our lab was we didn't have any speech experts. We still really don't have any speech experts. So we decided that since we don't have any experts, then we'll have the data kind of guide us. So if we knew, we kind of, I wouldn't say knew, but we were confident that if we could get a lot of data and we knew how to train really deep networks, then we will be able to build these systems. So one thing that kind of was a challenge for us, at least in the very beginning, was we had to do a lot of experimentation, and we still do at scale. To give you an idea, typically a publicly available data set, I think the largest one is 3,000 hours. And we typically do all our experimentation of multiple of tens of thousands of hours. So it's an
Wow.
order of magnitude. Yeah, so it's an order of magnitude difference. And
this is hours of speech data that we're talking about.
Hours of speech data, yes. So it's millions of training examples, essentially. So typically around 14 million utterances is about 10,000 hours, if that gives you an idea. So we have many millions of these training examples that we need to train our networks on. And we know that in deep learning is a very empirical field. I mean, nobody tells you that this is the network. You have to kind of hunt around and figure out what the network actually is. Which means running a lot of experiments. Each of our experiments takes anywhere from 20 to 50 exaflops. So that's like, exa is 10 to the power 18. So it's a lot of flops for one experiment. And typically we would want to finish an experiment within 3 weeks is pretty much the patience we have. So early on, we had to build these systems that is very, very high performant. And it still is, in my opinion, from what the numbers I've seen, is the fastest training system in the industry by at least twice as fast as what the best number I've seen publicly so far. And we kind of had to invent this thing because there was nothing when we started in late 2014, around October of 2014 is when we started, September, October, that time frame. So we built this thing, and I think we still are ahead. And what we are doing is slowly kind of open sourcing parts of this framework. So we want to kind of take our ideas and in some sense infect the field or infect the community with all these high performance computing ideas, which I think are very, very appropriate for deep learning. Deep learning is this problem that needs a lot of compute. And that's kind of what also differentiates our group is not only do we do deep learning, but we do this deep learning through this very high performance computing approach. And we do all our experimentations at big scale, which kind of separates us. And other people are catching on. I mean, you see now Google and Facebook and others have a lot of data have kind of come around to this kind of high performance centric approach. Yeah, and one funny thing, there's an anecdote, and this is true, I like to tell, is when we first started training in Mandarin and built a very decent Mandarin ASR system, not the best, but very decent, there was not a single Mandarin-speaking person in the group.
Wow.
So this is the power of data. You can look at a training curve and you know that if the training curve is going down, you're doing well. I mean, you don't need to know the language.
Right.
So my colleague Ryan Prenger, Ryan started doing it over, I think, the Christmas of 2014 when we got our first big Mandarin data set. He started training and immediately we started getting very good results. And
That's
we were
incredible.
like, oh my God. And essentially the same network architecture does both English and Mandarin, which, kind of validates your belief that the neural network will learn the differences in the languages by itself. And English and Mandarin are very different languages. I mean, they're so different, and the fact that this almost the same neural net architecture does both is still, to me, I've been doing this for 2.5 years. It's still, to me, one of the biggest surprises, and kind of validates our approach that let the data guide you.
So when you're approaching one of these problems and you're trying to kind of iterate to a neural network architecture, where do you tend to start? Do you start from published research like, GoogleNet or one of the, published network architectures that is kind of known good in a given class of problem? Or, at this point, do you have, your own best practices or proprietary network architectures? How do you tend to approach the network architecture problem?
Yeah, that's a very good question. And speech is a little bit different from identifying images, like you said, an ImageNet, the GoogleNet kind of architectures, which are stacks of convolutional networks, because speech has a time dependency, right? You can think of a speech as a sequence of audio samples. Typically, a good practice is to choose audio samples that are 10 milliseconds each. So every 10 milliseconds, you've got to get an audio sample. But there is a time dependency, right? Because what you say, at time t equals something is dependent on what you said, t minus something. So the styles of network that we had to train was what are called recurrent nets. And recurrent nets have been actually around for a long time. But when we first started in 2014, I don't think anybody had used recurrent nets that widely in speech, but we kind of had a gut feeling that since recurrent nets capture this time dependency, that's where we should start. So we started off doing very vanilla bidirectional recurrent nets, which actually bidirectional means they go backward and forward in time. So there's one layer which goes backward, multiple layers which goes backward in time, and other multiple layers which goes forward in time. That's kind of where we started off with. And Auni Hanoun, who is now back at Stanford, he had done some initial work on speech, and he had played around with recurrent networks a bit. So he was the proponent of using recurrent networks. And since then, we have evolved. We've used gated recurrent units, which are a little bit fancier recurrent networks, LSTMs. On top of that, you can use even fancier constructs like attentional models, which kind of look at capturing some sort of memory inside these networks. I mean, these networks, in some sense, are capturing memory of what you've said in the past. So yeah, I mean, you kind of look at your problem, and then there are wide classes of these networks. So convolutional networks kind of capture features in kind of an image space, in a 2D space, right? And these recurrent networks kind of capture features in time dimension. So depending on where your problem lies, that's where you would start. Like, for example, tomorrow, I have to, I'm trying to do something in video. Where would I start? I would probably start with recurrent networks as a first guess, because video also has a concept of time. So that's kind of where you start off with. And nothing is actually proprietary. I mean, one good thing about the community is people are very open about sharing architectures. Like, all our architectures are public. I mean, we publish yearly, almost at a yearly cadence, what networks we have been using, and they're all like standard known networks, just the architecture is different, like how they're connected, how many layers, what is the cost function, and so on and so forth.
So what's the relationship between the network architecture and the underlying systems that support them?
That's a good question. Typically, a lot of people, I think, because GoogleNet and because ImageNet has become such a widely known competition, that people focus on these stacks of convolutional nets a lot. Recurrent nets, because they go in time, they're a little bit difficult, because say you have a really long audio transcript, which means it will be kind of unrolled in time. You can think of it as a for loop. So depending on how long the audio transcript is, you have to kind of unroll that loop in time, which makes it a little bit more challenging compared to like convolutional networks. So their memory kind of blows up because you have these long utterances that you're transcribing. Sometimes your deployment can be a challenge because you're doing these small matrix multiplies, which are not very high performant, depending on how you do the inference. Inference is when you actually deploy these models. And you're also, and users are also very, very sensitive to latency. So which means you have to do it like when you're talking to Siri, for example, you spoke something to Siri and Siri took, I don't know, 1 minute to answer. Obviously, you're not going to be a very happy user.
We've moved on by that point.
Yeah, exactly. So you have to think about all these issues when you're doing inference for these kind of recurrent networks. And then very recently, there are network architectures that are incredibly challenging, things like WaveNet and ByteNet, which came out of Google DeepMind, and Pixel CNN, Pixel RNN. So what these networks are doing, they're generating one sample at a time, and this sample is at a very fine time granularity, which means they're generating one sample every 61 microsecond, which is basically 16,000. 61 microsecond is basically 1 over 16,000, so like a 16 kilohertz audio. So these networks are used to synthesize to the opposite problem. So given a text, you're synthesizing speech. Then you are incredibly latency bound. Like you have to generate an audio sample every 61 microseconds, and this entire network is like 40 layers deep, 50 layers deep, something like that. So this is actually a research frontier. Like, how do you make things like WaveNets and ByteNets synthesize things? Same thing happens with pictures, like the Pixel CNN paper. If you look at, I think it was presented last year's ICML. They're synthesizing images 1 pixel at a time, and to generate each pixel, you have to do this inference through this really deep network of 40, 50 layers. Which makes this very, very challenging. So from the system side, I think these networks are kind of at the forefront of difficulty and challenge of deploying these kind of networks.
Now, having been in the field for so long, does it still amaze you that any of this stuff works?
On a daily basis, and I think it's an Achilles heel in some sense that. The interpretability of these networks is extremely hard, especially for speech. I mean, if you look at some of the work that has happened in GoogleNet kind of world, where you can kind of deconvolve a layer and kind of say, okay, this layer is detecting like a face, this layer is detecting like the chin or something. Because humans, we are very rich. We can look at these patterns visually. I have no idea how to visualize a recurrent network. So how do you visualize an audio form? I mean, I don't know.
Right.
So because audio has in some sense much less information compared to like a image, like it's literally as a picture is 1,000 words, right? So in our domain, it's almost impossible to gain any sort of interpretability in the networks we train, which makes our life really hard because we see, I mean, almost every daily basis we see these something we see that is like, how did that happen? And it's very hard to gain insight into these networks. They're very much a black box, which makes them quite hard.
It's incredible to think that the neural network is looking at milliseconds of speech and is able to do anything with it. Let alone create words and have them be partially intelligible.
Yeah, and it's doing for 2 languages, which are completely unrelated. I mean, we do, like when we first started Mandarin, people were saying, oh, you need to do explicit tone modeling because Mandarin is a tonal language and all that stuff.
Right.
And you're like, we are not linguists. We are not language experts or speech experts. You're like, no, we are not going to do it. And we're going to just try kind of the quote unquote brute force method of like feeding it to the neural network and see if the neural network can figure out the tonality of the languages. And it does. I mean, if you ask me what layer of the neural network is learning these tones, I have no idea.
Well, I had a guest on the show, Pascal Fung, who spent quite a bit of time in her career working on speech, and she quoted, I forget the name of the researcher who's one of the pioneers in statistical modeling of speech, who said something to the effect of, my speech recognition accuracy goes up every time I fire a linguist from my lab or something like that.
Yeah, that's a very popular saying, and we kind of jokingly say it inside of our groups, especially when we first started and we had like no clue what to do whatsoever.
So your accuracy should be at the top, right?
But I think that as you get, going from say 80 when we first started, I think we were 80% accurate or 75% accurate. Going from that to 95, 96% is actually easier than going from 96% or 99%.
Oh, of course.
It's that famous sigmoid curve, right? I mean, you have to do 10x more work to get, I don't know, 1% more better accuracy.
Right.
Because making Andrew Ng gives this really nice example that it's very hard to build systems that are better than humans in accuracy, because then you kind of lose sense of like, normally when you develop the systems, you kind of get a sense of why the system is failing. Maybe the system is failing because it has background noise or something like that. But once it gets into the range where the humans will make mistakes, but then you can't judge something that is already better than you, because then you don't know what these failure cases are.
Right.
So the last 3% or the last 2% is really hard to bridge, and that's kind of where we are now. And it's becoming like increasingly hard. We're making progress, but it's not as rapid of a progress. We are. We want to close the gap, and I think we can close the gap, but it's going to be incredibly challenging. And the flip side is I don't think until you get to that 99% accuracy level, you can't really have a technology that kind of gives you the sense of magic, right?
Right.
It just works.
Right.
You're not there yet with ASR.
Right. It's amazing how close we're getting, though.
Yeah.
You said a couple of things that I thought were pretty interesting that I'd like to go back to. One was that you were starting to see results that were 2x better than what you were seeing publicly. Were those results in terms of accuracy, or I think it was training time that you were? What were those?
So those were training times.
Training times, right?
Our training. So from the very outset, what we have focused on was not just absolute training time, but one thing that I learned from NVIDIA while I was at NVIDIA is what is called the speed of light. The speed of light is basically, under ideal circumstances, what is the fastest you can go. And that typically is if your processor is running at full speed all the time, which obviously doesn't happen. So then what you should aim for is what fraction of the speed of light are you at? And typically for any real-world application, especially for applications that run for 3 weeks, if you're at 50% of speed of light, which means a GPU has a speed of light of typically around 6 teraflops if you take a Titan X GPU. So if you can sustain 3 teraflops, that's actually incredibly good. So instead of focusing on absolute training time, we look at what fraction of speed of light are we. Because that's a good measure of efficiency.
Right.
So we targeted 50%. And I just saw, I think, a paper a couple of days back, I believe from Google. It's a very good paper. It's on a mixture of experts. And they're, I think, getting around 25% efficiency. So the field is, in some sense, moving there, that people are caring about things like efficiency. Efficiency have been 25% of speed of light, basically. And we have been at 50% of speed of light since at least a year and a half. So in that sense, we have been 2x or more ahead of the field. And this is something that we as a group have been trying to kind of evangelize, that it's not just important to tell you the absolute number, but also what fraction of speed of light are you? Because otherwise it's hard to measure how efficient you are. And that's a different kind of thinking, I feel. And I think I actually learned it from NVIDIA when I was at NVIDIA, because as a game, when you're developing these algorithms for games, games also have this kind of a hard requirement that you have to generate a frame every 30th of a second, because typically a game would run 30 FPS, right? So then you need to do it very, very efficiently. Like a computer game, for example.
Right. And does your team, is it reflected in your team composition as well? Do you have more or folks from a systems background than you would typically find doing in an AI research group, or?
Oh, absolutely. So this was also something that is very unique to our group when we first started kind of formulating the lab. Adam Coates and Andrew kind of understood that the systems would be a really important aspect of deep learning. So we have a really deep bench in systems. We don't have a lot of people, but the people we have in our group, I think combined, have like 30, 40 years experience in building very, very high performance systems. And it's also a unique opportunity because there's a group that people can wear different hats, in fact, encouraged to wear different hats. So I come from a GPU background, other people come from GPU background. We learn about speech, about deep learning, about ML, and then ML people and the deep learning who come from the ML or more ML DL background, they learn about how to build these systems. I mean, you can't just write code and hope for the best. I mean, depending on what code you write and how you write it or how you architect it, your training run might take 2 months instead of 3 weeks.
Right.
And good luck with that. So it's a very interesting composition of our lab, and I don't think it exists anywhere else. But I think other people like Google, Facebook, etc., they're all seeing the value of this kind of an approach, and they're all kind of ramping up. The TensorFlow team is incredible, and they're also have a lot of really great systems people, and they've kind of realized the value of this as well.
It's interesting. I had an opportunity to hear Andrew speak at this conference that I was at last week. It was a GigaOM AI conference. Mm-hmm. And one of the things that he said that was really interesting was that, in Silicon Valley, we've got various established practices for, lots of things, building web apps, building mobile apps, building back-end infrastructures for those kinds of systems. Like even in spite of how fast those things are moving, like we have these established, principles and architectures and DevOps, we've got a team composition that kind of works. And in AI, we're kind of inventing all that stuff over again and don't have, everyone's doing things differently, trying to experiment and figure out what works and what works best.
Yeah, I think that's absolutely true. I think there is a notion of what an AI product should be, but I don't think AI products have had their what I call the Photoshop moment, right? The Photoshop was one of those early desktop apps, so to speak, which kind of defined what a desktop application should be, or a WordPerfect, or the early days of Microsoft Word, where these applications which defined what a desktop publishing or a desktop content generation application should look like.
Right.
I don't think AI product has had that defining moment that this app or product or service, people will say, "Oh my God, this is how AI products and services should be built." And again, there's a lot of experimentation. There's a lot of experimentation in personal assistants, bots, things like Siri and Google Voice, and our services in China of doing ASR. But I don't think I don't get the sense that we have had that Photoshop moment yet.
Mm-hmm. So another interesting point you made early on was talking about, you talked about some of the deployment challenges of the neural networks that you work on. And we often overlook those. Like a lot of the conversation, I think, is around training and the training challenges just because it's so time intense. But you mentioned some of the matrix multiplication challenges and other things. What do you find to be, how do you address those challenges, and how do you more fully characterize them?
Yeah, I think the deployment challenges are driven quite a lot by the application themselves. Like, as I said, any kind of service like speech, or for example, you're doing image tagging, for example, in an app, for example. Let's say an app lets you tag pictures of food or something. Users care, like all these services are very user facing, and our attention span or what we expect from a service has decreased over years. Like we really want everything to be very, very snappy, especially for things like speech, right? Speech is like our interface. Like when I talk to you, I expect an answer. I don't expect a silence. Like you're not going to speak to me after a minute after I finish speaking. So latency becomes really, really important. And then this is a challenge if the models are deployed in the data center, because if you're using a mobile phone, then you have to take into account the time that takes for the request to come to your data center, and then you run the model, generate the output, whatever you want to give to the user, and then you send it back. And for speech, it also depends on you're taking a speech segment and converting into text. Like when do you start chopping up these speech segments? So to the user, it feels like it's a completely seamless kind of interaction. Ideally, you would want these models to be pushed out to the edge, right? I would want my speech recognition engine, the ASR engine, to be running on my phone. It has not quite happened. So what people do is they take kind of a split model where a part of the model is running on the phone. And the reason you can't run it on these devices is because usually they're so compute intensive. I can actually take our model and run it on the iPhone or Android phone or whatever, a top of the line Android phone. But I can bet you that I'll drain the battery in like 20 minutes. And that won't be a very happy user, right?
Right.
So people kind of split the model. So maybe a part of the model that does Hey Siri or Hey Alexa or whatever is resident on the device, and that only does that bit. And then whatever you say after Hey Siri gets shipped up to the cloud and then transcribed there and then brought back. So those are the so I think more and more as the devices get more capable, and the other thing that people are also looking at is these neural networks are very over parameterized. Typically a neural network would be, say, 100 million parameters. So after you train it, it turns out that you can actually shrink it down a lot. You can compress these models down to really small models without losing a lot of accuracy. So people have been, and we are doing it as well, taking a network and shrinking it down and seeing if we can deploy it to an edge device. And going back to the matrix multiplies, in training, what you do is this thing called mini batching, right? So in mini batch, you take a bunch of training examples, shove it into like one big matrix, because big matrices are easier to get very high performance on. When you're doing speech recognition in the cloud for user-facing services, you can't really take a lot of utterances and shove it into this large matrix, because then you have to wait. And users don't like to wait. So then you have this problem of then you're ending up multiplying what I call skinny matrices, having one or two examples, which are not fast. So then you have to kind of write these special matrix multiplication routines that are not optimized for fat matrices or normal matrices, but for skinny matrices. And everybody's doing it. Google has a team, I believe, who does this kind of coming up with special libraries which are optimized for the skinny matrix multiplication. We do the same. So yeah, the training side is kind of a different world, and it's its own kind of challenges that I think doesn't get talked about a whole lot. But it's also extremely important, because this is where this is where kind of the rubber meets the road, right? This is where users start using your model to do something useful.
Right. The architecture you were describing, or at least the end goal of the architecture you were describing, starts to sound a lot to me like, almost like if you think about Hadoop land, and one of your first slides in your presentation was a picture of the Hadoop elephant, right? In Hadoop land, there's kind of this, migration from batch processing, MapReduce, to Spark and streaming processing. It almost sounds like you're describing a similar migration that many AI apps are taking or will need to take over time.
Yeah, I think I haven't heard that characterization before, but that is exactly right. Increasingly during when you deploy, it's some kind of streaming, and when you're streaming, you are very, very latency sensitive, especially if there's a user that's using the service. And typically during training, you are batching stuff up into these things called mini batches to get much more computational efficiency. And typically, I think one of the first lessons I learned when I joined grad school is my advisor said, latency problems are really hard to solve. I mean, if a problem has high latency and users care about low latency, those problems typically end up taking a lot of engineering effort.
It's harder to parallelize your way out of a latency problem.
It is very hard. I mean, you have to think about different algorithms, and it's or like different hardware. It's a mess. Like if your problem is bandwidth challenged or flop challenged, you can solve it relatively easily than trying to solve something that is latency challenged. And users care about latency. I mean, if we want stuff to work instantly. We have very little patience for something that is, especially for things like ASR and these kind of things.
Now, one of the techniques you described in your presentation was the graph transformation of some of these problems. Can you talk a little bit about the problem space there, the motivation, and what you found?
So I think it was pretty forward-looking. In fact, after the talk, I met some people who said, you guys are 5 years ahead of the field. Nobody cares. So what's really happening?
That's sometimes a good place to be, right?
So what we are seeing is you can think of a neural network as a execution graph. I mean, execution graph has some operations that you're doing in the nodes, and then you're sending some data across the edges. It's a very generic way or very flexible way of saying what you're doing. What we have found out is as we develop these very, very interesting architectures, they are becoming pretty hard to scale. So typically what we would do is we come up with a really interesting architecture, we start training in TensorFlow or any of the different frameworks, because specifying these architectures is very easy thanks to the work that all the different tool vendors have done. We have excellent tooling for specifying architectures. So we get up and running, we are training on, say, 1,000, 2,000 hours of data. And now we need to scale to what we call, our native data sets, which are tens of thousands of hours. Making this jump from where you're doing experimentation on a couple of thousand hours of data to tens of thousands of hours of data becomes very, very hard, because once you have to take these kind of graphs, which TensorFlow calls graph dev, and various tool vendors have their own name, into a bunch of cores. I mean, you can think of all these GPUs as a bunch of cores, and inside the GPU there's also another bunch of cores. This mapping gets incredibly hard. So what we do is then a bunch of people, we get together and try to hand tune it, hand map it down to these kind of cores. Usually it takes us anywhere between 8 months to a year, where we can take the networks that we want, that we are training on, say, a small amount of data, which is a couple of thousand hours of data, to like massive amounts of data through a lot of hand engineering, hand tooling, which ideally I want to shorten it. Ideally I want to shorten it to 2 months, where typically you're looking at, say, a WaveNet or a ByteNet or a attentional model, which are just very, very flexible, very interesting architectures, but also very complicated to scale. So that's what I was trying to get at, is like we really don't have this kind of intermediate layer which takes a graph specification from a framework, be it TensorFlow or MXNet or PyTorch or Torch, and takes this graph and then kind of efficiently maps it down to your GPUs or CPUs or what have you, and scale transparently. I mean, today you are doing an experiment on 1 GPU, tomorrow you flip a switch, you're doing an experiment on 64 GPUs, and you see no performance hit whatsoever. We just don't have it, and now it's a very extremely painful process. And then this really kind of gets at productivity of a group. I mean, we do it because there's no other way, but ideally it's kind of a wake-up call for the community to like come together and kind of build this software tooling or the software middle layer that's absent.
Mm-hmm.
And as I said, in full generality, it's an intractable problem. So you have to like figure out what sort of restrictions you want to place, so you can you can kind of do both things. That you can get the flexibility of looking at the networks that you want to look at, and also be able to like scale these networks out to the data set that you want to scale at. And they're usually opposing goals, so you have to like carefully figure out what compromises you have to put in the system.
Let's talk a little bit more about the 8 months and what goes into that. Is it that it's a computationally iterative approach to solving this problem, meaning you've got this model that, after, one computationally iterative, cycle of, training a model and coming up with a model that you think works, you then are having to, run it at scale, figure out where it breaks, tweak it. And then are you remodeling, I guess? Are you retraining in that process, or are there other steps taking place to get to a model that runs at scale?
And no, it's usually the same model. You just have to re-implement it. Say you take an attentional model, for example. These are pretty complicated models.
Mm-hmm.
And typically what happens is you run out of memory. Because these models are large, there's so much intermediate computation and so much intermediate state that you have to save. You make the models larger. I mean, when I say the models larger means the individual layer sizes changes. So the connectivity stays the same, but the individual layer sizes, say, go from in a dimension of say 256 to say 1024. And when you increase the dimension, stuff increases by a square, right? Because it's a matrix.
Right.
So now you're suddenly out of memory. And then if you're suddenly out of memory, you can't run on the GPU. And then you have to like look at the graph of this and figure out, typically, as I said, every edge in the graph is something that stores memory. You need to figure out, okay, I need to collapse this graph. And collapsing this graph essentially means writing a new program. Mm-hmm. Because you can think of the nodes as essentially small programs, like a matrix multiply or something. Mm-hmm. So then you have to start fusing these nodes in some interesting way, or think about, how do I partition this graph over two different GPUs? Because right now this entire graph doesn't fit on one GPU. So now I have to partition this graph over two GPUs. So as soon as you think of partitioning a graph over two GPUs, it's like, okay, how do I communicate?
Right.
So all these, problems start coming up. It's extremely handcrafted in that sense.
Right. I understand. It sounds like you're starting with this, this model that you've constructed using these tools that isn't necessarily designed for scale. And then you systematically have to, if we were thinking about this in the context of traditional compute, you systematically are denormalizing your database, distributing out, and rewriting everything in assembly.
Pretty much. I mean, at the end of the day, for some of the networks, we just have to rewrite in assembly because they're not fast enough.
Yeah.
Otherwise, so it's a very it's almost like an artisan chipping away at a problem. And in some sense, I mean, as soon as you have an artisan chipping away at a problem, it doesn't scale, right? It's like it slows you down. I mean, that's why we invented compilers, because people were, tired of writing assembly by hand. Mm-hmm. So that layer doesn't exist.
Mm-hmm. It's interesting to think about, as we think about general AI and the path to getting towards, to having in existence, a totally generalized AI. Mm-hmm. I think we think about a lot of things, but I'm not sure that, in that conversation, at least I've not heard it, explicitly called out. In order to do that, this system is going to have to be on the cloud, in the cloud. It's going to have to be massive. It's going to have to be trained on massive amounts of data. It's probably not going to be, well, there's certainly a lot of algorithm work that needs to be done and lots of other types of work to be done, data management, et cetera. Yeah. But, there are huge systems problems, fundamental systems problems that, we're so far from solving.
So that's why I was trying to say it's kind of trying to it's a wake up call or whatever. I think one of the problems also is we as a research community have done a fairly bad job of having massive amount of publicly available data set. The only big publicly available data set is ImageNet, and the architectures to do well on ImageNet are actually fairly simple. Mm-hmm. We know how to run them fast, very fast. In fact, I would not be surprised if ImageNet-like networks get embedded in an ASIC and be available in your phone or your camera and whatnot.
Right.
But a lot of the problems that we deal with in speech generation and speech synthesis or speech recognition, in language understanding, there are no public data sets. There are no public data sets that are big. So people do. You look at the research that happens in network architecture exploration. If you look at the papers that come out in ICLR or ICML and NIPS, they are all working on really small data sets. So they don't face the challenge of scale. And I don't blame them. It's not that they're doing it purposefully. Just no data. So that's also, I think, is a challenge that I didn't talk about in that talk itself because it wasn't the right thing. But this, I feel, is a really big challenge that we don't really have good, large, publicly available data sets for stuff that's not ImageNet. Because if you are thinking about AGI or whatever, we need a lot of publicly available data where we can actually scale, unless we come up with algorithms that will work at small scale, which people are working on that too, but we haven't made as much progress as we have in other fields. Mm-hmm.
I've heard someone describe this problem to me as the industry having overfitted on ImageNet and some of these other data sets.
I totally tell that. I tell that to people, like whoever is willing to listen, that look, you're overfitting on ImageNet. I tell that to every vendor we work with. They came we work with a lot of different hardware vendors and stuff, and they all come up with all these results that look, we are XYZ fast on ImageNet, and we don't care.
Right.
We just don't care. It's a solved problem. ImageNet is solved. It just did. As I said, it's solved enough to the point that I expect to see it in ASICs.
Mm-hmm. Yeah. Wow. So we're getting close to the end of our hour, but I'd love to hear you talk through. Actually, I had one more question related to the stuff we were talking about. So, all of these system things that we're describing, what's the best way to ask this question? You have an HPC background, which is, I think, increasingly rare in in a world where people are coming up from kind of web-based architectures. And I don't hear a lot about that in deep learning necessarily and machine learning. Can you talk about how that kind of thinking has influenced what you've done and where you're directly pulling from HPC? It's been a while since I've been involved in the HPC community, but does it lead you, for example, to use InfiniBand and some of the exotic HPC stuff, or how does it influence you?
Oh yes, InfiniBand is not exotic in our world. It's pretty standard. When we first started building stuff, we started using InfiniBand. So the HPC kind of thing is, as I said, is efficiency and speed of light is extremely important to us. So as I said, the first thing we think about is how efficient we are in terms of the processor flops. So if the processor is, say, as I said, 6 teraflops or 7 teraflops, how close to that number can we get over a period of time? It just doesn't have to be bursty. So if you say that, I can reach 7 teraflops, but I can only reach it for 2 seconds while my whole application takes 2 hours, that's no good. So how much can you sustain over the entirety of an application runtime?
Right.
Which, as I said in our example, is in many weeks. So that's, I think, the driving kind of HPC thought is how efficient can I get? And when you think about efficiency, you tend to build systems that what I call are tightly coupled, which means a loosely coupled system is kind of a web style system, right? You have this,
Right.
1U blades that are connected by probably a gigabit Ethernet or maybe 10 gig. I don't know. I think it's still gigabit. But we build like really fat nodes. Like each of our node is like 8 GPUs in it because we want these computing elements. If you think of a GPU as a computing element, we want them to be as close together as possible because we know that there's a fundamental physical limit on how fast you can move electrons over a wire. So if you want to move stuff fast, you want the wire to be very close to each other. Similarly with InfiniBand. So InfiniBand, we have like InfiniBand switches in our rack. So we don't have many racks. But each of our rack is pushing like 30 kilowatt of power. And then a typical data center rack in Google, Facebook, or even us. I mean, in our we have huge data centers in China for web style workloads. They are like at less than 10 kilowatts.
Right.
So it's a very different kind of mindset, which is a mindset that, okay, I need to push orders of exaflops. So if I have to push orders of exaflops, I need to be maximally efficient on my system, and I have to build systems that have very small distances to transfer data, like really short wire distances. So you tend to build what I call fat nodes that are very closely connected to each other using usually InfiniBand, or Ethernet is also catching up. But there's also I'm also telling somebody that I would like to see more research in interconnects, because low latency interconnect is becoming really important with deep learning. And you see research in that with not only from InfiniBand from Mellanox, but also from NVLink from NVIDIA, and then OmniPath from Intel. And I think we will see more and more of these low latency interconnects for workloads like deep learning.
Great. So you tell me, based on your time, do we have time to run through the latest in GPU and?
Absolutely.
Okay. Awesome.
Yeah.
So maybe we should start with at the highest level, the evolution that you've seen and how folks are applying GPUs to these types of workloads, why they're important. Frameworks, QDNN, I can only assume is related to the CUDA stuff that you were working on. Like, how does all that stuff fit together?
So it, in some sense, deep learning is a problem area that is squarely in the comfort zone of the GPU, because if you look at the fundamental operation in deep learning, it is regular matrix math. And if you look at graphics, it is also regular matrix math, and it's smaller matrices, but it's also matrix math. So if you have dense matrix algebra, which is what essentially deep learning is, almost every operation in deep learning is a dense matrix math. It's squarely in the comfort zone of the GPU, and that is why GPUs are doing so well in this space. And then toolkits like cuDNN is essentially taking things like these special convolutions. I mean, a convolution is, in some sense, a dense matrix math, which is how cuDNN does it. So what cuDNN is doing is taking these special kind of convolutions that can be in 4 dimensions that is used in deep learning and putting it in a library, which is exactly the right thing to do. Because they're different from the convolutions that's used in, say, traditional vision or traditional graphics or so. So these are special kind in that sense. And then what cuDNN is doing is also kind of moving up the stack. For example, now cuDNN has a GRU implementation, for example, a batch norm implementation. So in some sense, I think cuDNN is going to do a pivot and change its name, because it does a lot more than just convolutions and stuff that's used in ImageNet, because more and more they're putting in stuff that's used in recurrent nets. And then you have these frameworks like TensorFlow and PyTorch and MXNet and Theano, and many more. There are probably 20 odd frameworks that layer over these frameworks like cuDNN, like MKLDNN that I think Intel has. And then what these frameworks are doing is lets you kind of very easily specify this network architectures like an ImageNet or a WaveNet or a ByteNet or attentional net or a recurrent net. And you can think of each one of the nodes in these networks as something, as a call into cuDNN in some sense.
Okay.
And they're all in Python because Python has kind of become the de facto kind of language in the AI world or the DL world.
So CUDA itself is the API for programming the GPUs, basically.
Yeah, so CUDA is both. CUDA is a big thing. I mean, different people think of CUDA as different ways. CUDA is also a language in some sense.
Okay.
It's got a little bit of its own syntax. It's very much like C, C++, and a little bit more syntax. So CUDA is this whole, like, you can, so you use that, and it also has a bunch of API calls that you call into the GPU. So it's both like a programming framework as API and also this language itself for programming the GPUs. Yeah.
Okay. And then cuDNN sits on top of that to provide higher level primitives for programming deep neural nets. And then the frameworks, Torus, Theano, TensorFlow sit on top of that.
Yep, that's exactly right.
Okay.
And cuDNN could be written as in CUDA, definitely written as in CUDA. You can also, I mean, for reasons of speed, you can even write in assembly, which they might have done. But yeah, that's the right picture to have in mind. It's CUDA, cuDNN framework, going from bottom to top.
Okay. And so where do you see things going on the hardware side? Intel is trying to work on some things. Google has their tensor processing unit. How do you see all that stuff evolving?
Yeah, that's a little bit of a hard question to answer because the future is kind of unclear in some sense. I mean, the sense that the network architectures are evolving so fast that it's kind of hard for the processors to kind of keep up. So far, what has happened is, everything is this nice matrix multiply thingy that works really well on GPUs, but we do have networks that are actually pretty hard to do on GPUs. For example, WaveNet is one such network. So I think for the chip vendor, I mean, ideally you want both to like co-evolve, like the hardware architecture would evolve with the network architecture. But the problem is it's very easy for me to come up with a very interesting looking network using TensorFlow, but it's very hard to build hardware. Building hardware is this incredibly resource intensive, money intensive process. So it's a little bit hard to see where the hardware is going to evolve. I think the way NVIDIA and Intel are approaching the problem is, okay, let's just make it fast for matrices of some sizes. And we have this benchmark out called Deep Bench, which tells what matrix sizes it should be for some of our networks. And then Google has developed TensorFlow, which it's not a lot of details out, but what I suspect it is more towards inference and doing very low power inference, but not so much for training for some specific models. So you could, as I was saying, that as networks like GoogleNet and things like that mature, you'll probably see them burnt into an ASIC and then shipped into a phone or a camera or wherever you're doing some kind of image or object segmentation. So yeah, I think people are kind of just hedging their bets and trying to see how the networks are going to mature. And it kind of affects both ways because I won't make a network, I won't come up with a network that is not efficient on any processor that I can run on. If you get what I mean.
Right. So you have no incentive to push the envelope for the hardware folks, and the hardware folks have no incentive to push the envelope because they don't have any networks to run on their stuff.
Right. So like, I wouldn't say no incentive, but I would say they're both looking at each other kind of warily. Right.
Who's gonna dump the billions into this science project kind of thing?
Exactly.
Yeah.
Because
it's an interesting spot to be in.
Yeah, I mean, it's going to cost billions. I mean, let's not kid ourselves. I mean, that's what it costs to build, like
fabs and all of that stuff.
Yeah.
And one of the issues that comes up, at least in Intel talking about Knightsbridge and their advanced processors that are trying to solve this problem, or at least, cut off NVIDIA at the pass, is the issue of floating point versus innate. Like, can you kind of talk through what that's all about?
Yeah, so reduced precision is this really interesting thing, and this is also why I feel the industry is optimizing towards GoogleNet. So we have been trying to do reduced precision for 2.5 years. And doing reduced precision, like which is what int8 is, instead of say float 32 for recurrent nets like speech, is incredibly hard.
It's hard.
It is incredibly hard.
So I thought, just to jump in here, what I had envisioned this as a simplification of the chip that allows Intel, for example, to stuff more, to make a given silicon die able to do more math. I hadn't really thought of it as something that's harder. You're basically float 32 is your 32-bit floating point.
So when I say hard, I mean getting it. So if I say train a network in reduced precision, say float 16 or int8 instead of float 32, that network will not perform in terms of accuracy as well as a float network trained in float 32. That's what I meant. So if I have chips that can only do reduced precision, then it doesn't help me at all because my models don't perform well.
And why is that? I was under the impression that the reason why N8 was great, where using integers was great, was because the networks themselves don't inherently take advantage of floating point. Is that? I guess that doesn't really make sense, right?
That only makes sense in the GoogleNet world. This is why,
and thus,
it does not so far has made sense in recurrent nets. We may be seeing some light at the end of the tunnel. Very early days. Recurrent nets for speech, I feel, are some of the hardest networks you can train. They're very, very hard to train. In float 32, we have figured out quite well, but we have been trying for at least 2.5 years to do on reduced precision, and we have not been able to do it. And when I say have not been able to do it, what I mean is the models we train using reduced precision is not as good as the models we train using float 32. And if it's not as good, I'm not going to deploy. I mean,
right.
So that's I think reduced precision is another case of the industry optimizing on GoogleNet, which may be fine because they might have customers. All they want is object detection, say automated driving, for example,
right.
Object detection, object segmentation. So they have a market where they can sell these chips into. But it's not appropriate for all neural nets, especially not recurrent neural nets yet. I mean, we might be able to figure out how to do it, but we're not there yet.
And so I can make sure I understand when we're talking about training a network in float 32 versus N8, is the issue that between the neurons in our neural network, we've got these weights, and the weights are multiplied by states to give us outputs. Is it that the weights are integers versus floats, and or the states are integers versus floats? So all that. So in GoogleNet,
you have touched upon a very interesting thing. Like there are many things in the neural net that you can choose to keep in low precision. Do you want to keep the weights in low precision? Do you want to keep the intermediate state that you generate in low precision? Do you want to keep both in low precision? Do you want to keep only the gradients in low precision? I mean, there are many design choices you can make. And there are all kinds of funny, interesting, unexplainable results depending on what you choose to do when we train these networks for speech. Typically, at the end of the training process, you spit out a model, which is basically the weights. So typically, you just want the weights to be in low precision. But in recurrent nets, the convergence is extremely sensitive because you're doing this serial operation through time.
Right.
This is extremely sensitive to floating point error, to the point that if we take an algorithm and move from CPU to GPU, because floating point math is floating point addition is not associated, which means the sequence in which you do the addition, if it's different, you'll get a different number. So say you move an algorithm from CPU to GPU, you will get a slightly different result. And sometimes that can make and break a model. and that has happened with us a few times.
Wow.
Yeah, so that space is, I think, it's a field of research. Like, how do we think of floating point in this new world of training neural nets? And I wish people who deal with this kind of stuff, like the floating point committee or whatever, would research this more.
And in terms of the architectures, the GPUs are more optimized for the lower precision, but they also do float.
They're getting there. I mean, yeah. So typically GPUs have only done float because that's what games don't need anything better or more than float.
Okay.
And then GPUs started getting used in oil and gas, for example. Oil and gas needs doubles for the different partial differential equations they're solving. And then comes along deep learning. And deep learning is saying that I can do with float, and for things like Google Net, I can get away with int 8 or float 16. So the GPUs are now starting to support float 16 as well natively. Now the GPU vendors have to kind of target 3 different markets: one which uses float, another which uses double, another a part of the market that uses uses float 16 or int 8.
Wow, great. So this has been super interesting. Before we go, anything, what are you excited about? Anything that you're working on, or any asks for the community, the industry? How would you like to close us out?
I am personally interested a lot in speech synthesis. I think to build really natural interfaces, you need speech that sounds natural. We are far from there. Like, that's why you have this robotic voice that talks to you from various devices. I think there's a lot of research to be done on very natural sounding speech from all these devices that interact with voice. And going far out, I mean, I would really like to see conversation being a first class UI element with all the devices that we use.
Right.
Because, as I said, conversation is our UI. That'll be incredibly nice if we see it in, say, the next 5 years or so. It's challenging. It's going to be very challenging. So that's kind of my dream in some sense. And in the shorter term, of course, the systems goals that I talked about, like this kind of a middleware or middle ground where we take these graph transformations. It's starting to happen a little bit. TensorFlow has this thing called the XLA, which is really kind of the first step in that direction. The XLA compiler that came out with the TensorFlow 1 release that was last week, I think.
Yep.
So people are starting to take note, and hopefully we are not like 5 years ahead of it. Maybe things will get solved in the next couple of years.
Wow. Awesome. Well, Shubho, how can folks find you online? How can they follow the work that you're doing?
So the work that I do at Baidu, we have a website, research.baidu.com, where let me see if I have the URL right. And a lot of the work is there. I'm very easily findable on LinkedIn, Shubho Sengupta, SHUBHO, and SENGUPTA. I'm happy for people to get in touch with me, ask me questions, whatever. I'd be happy to elaborate. And thank you for your time and this platform.
Awesome. Well, thank you so much. I really appreciate you taking the time to join on the show, and I really enjoyed the discussion.
Yeah, me too. Thank you.
Thanks.
Bye.
All right, everyone, that's our show for today. Thanks again to Shubho for an amazing conversation. I hope you all enjoyed it. Once again, thanks so much for listening and for your continued support. Please remember that we want to hear from you. You can comment on the show via the show notes page, via the @TWiML Twitter handle, or my own @SamCharrington handle, via our new Facebook and YouTube pages, or just good old-fashioned email to sam@twimlai.com. Your likes and subscriptions really help support the show, so keep them coming. The notes for this show will be up on twimlai.com/talk/14, where you'll find links to Shubho and the various resources mentioned in the show. Thanks so much for listening, and catch you next time.